Hi, and welcome to our next section here, which is an extended comparison between the Lasso and Ridge. So we'll talk more about properties of Ridge and Lasso. Now we've covered already quite some ground. We'll talk about the so-called coefficient path plots, which help to analyze and diagnose these two model classes quite conveniently. We'll talk what happens under correlated features, and we'll also discuss a little bit why it's pretty much required to do feature scaling, feature normalizations for regularized models. Okay, so I guess that slide here really is a recap. So you can see the formulas of the constraint formulation of Ridge and Lasso on that slide. So we've already understood that in both cases, and if lambda is simply large enough, the solution which minimizes the regularized risk is usually always a point on the boundary of the feasible region, so like here, okay, or like here for the L2 penalty. As expected, both of these regularized minimizers, they have smaller parameter norms, so we call that parameter shrinkage. We've also discussed that for the Lasso, the solution likely touches the vertex of the constrained region. This induces sparsity, and we can exploit this as a form of feature selection, and we very often do that, especially in high-dimensional spaces for linear models. It can also be shown that if P is actually larger than N, so if we have more features than samples, the Lasso selects at most N features. So if you want to study that, have a look at the reference here included in the slides. Okay, I wanted to show coefficient path plots, so here they are. So again, I'm using a very simple example. We've used this before, this empty cars data set. And I'm running the Ridge and the Lasso both on that data set. And what we also will do is we'll fit the model for multiple different lambda values. And lambda is on the x-axis, so on log scale. And there's actually a way to do that for these two models without like running the model again and again. So you can compute all of the coefficients for a whole sequence of lambda values way more efficiently than doing this iteratively. Don't want to go into the details here. Yeah, I mean, you could also imagine that we would do this, this slow and inefficient way. Now, what I do want to talk about here is the structure of these plots. So, as I've said, lambda is on the x-axis. It's maybe you have to kind of get used to this a little bit. First of all, it's on log scale, and kind of the order of lambda is, well, no, actually it's not. I'm starting to confuse myself. It's simply on log scale. I guess what I want to say is, well, let's actually look at what's on the y-axis and what's in the plot. So here we have the coefficient values, so that each curve represents the coefficient associated with a specific feature as it develops when we wiggle, or when we wiggle the lambda, when we change the lambda, when we move from very large values to very small values. So if we move this direction here, okay, let me remove a little bit. So if we go from right to left, we start with a very large lambda value, maybe nearly infinity. All of our coefficients are basically shrunken to zero, and then they become larger and larger and larger because we leave room for them in the model by weakening the penalty. Or maybe it's actually a little bit better to read this from the other way, to read this from the other side. So here, lambda is 0, and we now start with the unregularized model. So both of these starting points should basically be the same for the L1 and for the L2 penalty, because the penalties are off at that point. And now we increase lambda, and what you can see is how parameters get shrunken. And for the Lasso, you can also see that they get pushed out of the model completely. So for Ridge, you can see that everything becomes smaller, but nothing really becomes exactly 0. For the Lasso, you can see these points here where features and parameters get pushed out of the model completely. And for reference, I've also shown here the mean squared error for the ridge and the lasso, you can see that we can definitely underfit these areas here where lambda just becomes too large and we over-penalize too much. There's no real overfitting going on. I guess you can maybe say that the curve here goes a little bit up. We definitely don't have something like this, which mainly happens because the empty cars data set is so low dimensional, so we can't really make the model, the unregularized model, overfit too much or at all. Maybe we can also talk a little bit about this here. So what's on the top of the plot. So there you can see how many active coefficients we have in the model, and I guess that's a further way of seeing that for ridge there are always 10 active coefficients, 10 active features in the model, while for lasso it becomes sparser and sparser. So at this point here, there's only three features left in the model, which I guess you could see better if I wouldn't have scribbled exactly on top of the 3. Okay, so because the data before the empty cast data set is so low dimensional and we can't really see any overfitting, correlation structure is also really simple. We created an alternative higher dimensional data set. It's still quite simple, also has a more correlation structure going on. So here's the model. You can see it's still a fairly simple model with a large effect for x1 and x2, a median effect of 5 for x3 and x4, and then for the remaining variables from 5 to 15, a smaller effect of 1, and then all of the remaining features, because we're using 50, so 36 of them are complete noise variables, so they have a true effect of 0. Putting some noise on top of things as usual, but now our features are actually drawn from a normal distribution with correlation structure. So you can see how things are correlated, well, the covariance value to be precise, and this is what is sometimes also called a Toeplitz structure, because if you look at the matrix here, this is constant on these major and minor diagonals, okay? On all of these diagonals, the covariance is constant. Yeah, you can easily see this here from this formula. Okay, this is sometimes people call this Toeplitz covariance structure because there are these Toeplitz matrices where things are constant on these diagonals in linear algebra. And now you can see that we do overfit at least a bit. There are these kind of optimal regions here for lambda. More interesting for us is what happens with the coefficient values. So for that reason, I have shown some histograms here. So here you can see the histogram of the L1 penalized coefficients, and here for the ridge. And what you should see is that, first of all, the histogram is a little bit broader. More values are non-zero for the ridge, and we have these high peaks here on the 0 for the L1. So again, we can see the feature selection property of L1, and you can see this especially for these yellow bars, which are produced by using a higher penalty of lambda equals 100. Okay, I also want to talk a little bit about, or I want to emphasize that we should always do feature scaling for regularized models. That doesn't only hold true for linear models, but for regularized models in general. Very often implementations do that by default, so we don't necessarily have to do this in code. I guess we should check, but it's always a good thing to understand why that happens and why that's necessary. First of all, smaller technical point, usually we do not regularize the intercept in our, so we don't include this in our penalty. The reason is that if we would use an infinitely large penalty, we don't necessarily want to penalize things so they result in the complete 0 function. Kind of the end of things should be the constant function. There's no real reason to push the constant outside of the model, and this is why this is usually not included in the penalty structure, but things can sometimes be implementation dependent. Now, back to feature scaling. So if you just look at the unregularized linear model, that has something that is called rescaling equivariance. That simply means if we scale some feature, we can simply anti-scale the coefficients and the risk does not change and the model really doesn't change. And we'll see an example on that exactly on the next slide. This is really not true for regularized model. So if we downscale our features, then the coefficients they have to become larger to counteract that downscaling. But if the coefficients become larger, they don't only counteract that downscaling in the loss in the ERM, they are also now penalized more strongly in the penalty, and now things become more difficult in terms of the result. So if you would do something like that, that would actually make the feature less attractive in the penalty. Yeah, and that changes the result. So usually the idea is to put features on a similar or on the same scale, which means we usually standardize things. So usually we do some statistical standardization where we subtract the mean and scale everything to unit variance. And you could do something similar. It's also not obvious which of these scalings would be optimal, but usually it's not good if features are on completely different scales. Here's an example so you can see this more directly. So we've used a super simple linear DGP here, 5 features. And you can see the coefficients, they just run from 1 to 5. It's just a super simple toy example to show that effect of scaling. And now, well, we have we'll look at feature 5, okay? That has a coefficient also of 5 here. And we'll now assume that our feature was actually measured in meters. And we'll just do a simple unit change, okay? We'll just express that feature now in centimeters. What does that mean? Well, we have to multiply everything by 100, right? To go from meters to centimeters. But I guess structure in the data doesn't really change by just going to a different unit, right? Here you can now see what happens with the OLS estimators for the unscaled data and for the rescaled data. And here with rescaled is this unit change, right? I don't mean standardization. So what happens? Well, only theta 5 is affected, and because we multiplied the feature values x5 by 100, the coefficient is simply divided now by 100, and the model is effectively the same. You can also see this at by considering that the MSE didn't change at all, and all of the other feature values are not affected at all. Now, if we do rich regression now, and we do this on the same 2 data situations, something different happens. So everything basically changes a bit. And you can also see here, maybe we can start by looking at what happens with theta 5. So what happens here is, of course, theta 5 becomes smaller to counteract the multiplication by 100, but it doesn't become smaller exactly by a factor of 100 because the coefficient value is now smaller, so it's penalized less. That's the opposite situation of what I explained on the slide before. It becomes small, so the penalty is not so strong, so we can actually get away with using a slightly larger value for theta 5. And you can also see that everything else is also affected, so all of the other parameters change. Also the MSE changes because of this. So we are not really fitting the same model. This would also indicate that, especially for Lasso, especially for very correlated features, we arbitrarily force a feature out of the model through basically doing unit changes. But this can happen even without strong correlation in the features. This can happen for arbitrary penalties. Well, not that you push something exactly out of the model, but by doing an opposite unit change, okay? Where you don't go from meters to centimeters, but maybe from centimeters to meters or to kilometers. So making the feature smaller, having the coefficient because of that becoming larger, you will make that feature more and more unattractive, yeah? And the penalized loss minimization just by doing this unit change, which shouldn't really do anything. And this is why we usually recommend to scale things before we go into penalized loss minimization. And this recommendation is not only true for linear models, it's also true for nonlinear models. Further example here for correlated feature structures. Again, very, very, very simple linear situation for the DGP. So we have 5 features. They have all the same effect of 0.2. I'll sample 100 values from that DGP with some simple noise structure here. I will now again create random feature values so that x1 to x4 are actually independent, but x4 and then x5 are actually strongly dependent. Yeah? So I've left out the concrete formulas here, but they don't also really matter. Here we can now again look at the coefficient paths for L1 and L2. What can we see? For L1, we can see that this, for also quite low lambda values, this will remove x4 pretty early on. L2 basically at some point for larger lambda values estimates pretty similar values for x2 and x5. So L2 keeps both things in the model, while the Lasso basically selects one of the two, so it pushes this thing here out of the model and estimates its coefficient to 0 and not to 0.2. So this is also sometimes called the grouping property. Yeah? So for ridge, for highly correlated features, ridge tends to have somewhat equal effects. The Lasso, however, decides which of these features to select, and the selection is somewhat arbitrary. Okay, so by bootstrapping the data, well, I don't know, adding a little bit of noise on it, it can actually happen that x4 is now chosen. Also, if you just look at this, I mean, the model, the effects of both features are pretty much the same here, right? There is no, I don't know, objective preference for either x4 or x5. It's pretty much random what is selected here by the Lasso, but one of the two will be selected because of the high correlation between the two features. So I guess we could discuss this a little bit more in detail. So this random decision that's being made here by the Lasso is more or less a pretty complex interaction between the correlation structure, specifics of the optimization method we're using to optimize the Lasso, the hyperparameters, initialization, and so on. And the theoretical reason for this behavior is quite strongly related to the convexity of the penalty structures we are using. So if you want to look into further details, have a look at this paper here. So we can at least do an intuitive explanation of this on this slide here. So if we look at these very strongly correlated features x4 and x5. So let's actually consider they would be perfectly collinear, okay? We can now gain some intuition what actually happens here. So if you look at the L2 penalty, L2 is actually strictly convex, okay? And this thing being strictly convex means there's just a single solution, and this is the reason for this grouping property here. So L1 is actually not strictly convex, so no unique solution necessarily exists, especially it doesn't really exist for this perfect correlation structure here. So we can have kind of a whole sequence of solutions of the same quality where the sum of the coefficient values of x5 and x4 are the same. So we don't have this grouping property. So as long as we are producing convex combinations here, these will all produce solutions of the same quality. Okay, so sorry for not proving this exactly. This is all done here in this paper. Take a look at this if you want to. Summary until here. So neither Lasso or Ridge can be classified as overall better. What you want to use depends on circumstances and depends also on the goal of your analysis. Lasso can shrink some coefficients to 0, so it selects features. Ridge usually leads to dense solutions with smaller coefficients. The Lasso is likely better if the true underlying structure is sparse. Ridge, on the other hand, works well if there are many weakly influential features. And both of these techniques you like using on higher dimensional spaces. Lasso usually has difficulties handling correlated predictors. For high correlation structures, Ridge usually dominates Lasso in performance. It usually is, I would say, in many cases, a bit better in terms of predictive performance in general. So I guess that's usually what I would use first and foremost if I would only be interested in predictive performance. Lasso is interesting for its feature selection property, which can also be generalized in many different forms to also select groups of features and so on. As we have said, and that's a little bit annoying if you like the feature selection property, but your features are correlated, then Lasso kind of selects an arbitrary features if things are very strongly correlated, and you could exchange things. But I guess that's what happens if you say I want to have a sparse model and features are nearly exchangeable. In such situations, the coefficients of correlated features in Ridge, they are usually similar. So I guess this is something to keep in mind when you use these techniques and when you analyze the results and interpret the results in the context of your task. Okay, this ends our section here. See you in the next one.